Hello aspirants, today we will discuss a brief overview based upon another doubt, which is what is the basic principle differences of application between stacking gel and resolving gel when it comes to SDS page. I guess most of you are aware of the term SDS page, which is polyacrylamide gel electrophoresis. And if we come across the basic principle, in this case, the gel is prepared, and there are two kinds of gels. One is the stacking gel that is required, and the resolving gel. Here, the major component is acrylamide as well as mixed acrylamide, and based upon the ratio of acrylamide and bisacrylamide, the gel is prepared. And the fact is, the pore size is determined upon this ratio. Now, the fact is, we all have come across the basic components that are used in a stacking gel and resolving gel. Almost all of these components are similar, which includes, irrespective of stacking gel or resolving gel, it consists of acrylamide, next it comes to tris, HCl, third there lies DH2O, fourth SDS, and fifth APS, then timid. Stacking gel and resolving gel, both of these consists of these components. Now, the percentage between these two gels vary. That means for stacking gel, it is about 5%, and for resolving gel, it is about 10 to 15% based upon the molecular weight of the protein that we are supposed to get. Now, what is the basic differences in between these two? Why it is 5% and why it is 10 to 15%, and what are the basic differences in components in between these two gels? We will discuss a brief overview regarding it. Now, all of these components are said. From there, acrylamide, as we have came across, acrylamide and bisacrylamide percentage, it determines the pore size of this gels. Based upon it, the electrophoretic mobility is established. The electrophoretic mobility of protein is established. Now, as the term electrophoretic mobility, that means there's a charge difference when it comes to protein separation. So, based upon it, first we will discuss what is the difference between these two gels and how this electrophoretic mobility works when it comes to distribution of a protein. These two aspects we will discuss in today's session. For tris HCl, when it comes to stacking gel, when it comes to stacking gel, the electrophoretic mobility is established based upon components that are present at a specific concentration and a specific pH. Now, the tris used over here, tris HCl, it has acidic pH with a pH of 6.8. And when it comes to resolving gel, the pH is about 8.8. What is the logic behind it? As we all know, when it comes to solidifying a gel within a cassette, what we usually perform? There lies, these are the wells present within the stacking gel. This is the entire stacking gel, and below this lies the separating gel or the resolving gel, and this is done within a cassette. Now, protein sample is added. When it comes to addition of a protein sample, when it comes to addition of a protein sample, after that, what you usually do? This entire gel is being kept within a cassette, and we use a running buffer. A running buffer. The basic composition of running buffer is glycine, tris, and followed by SDS. The purpose of SDS, it is to provide a negative charge within the protein all over the structure. If we come to the structure of a protein, suppose this is a type of a protein. Suppose this is positive, this is negative, this is again positive, negative, etc. And when SDS is added, what happens? The entire protein gets aligned in a, and within this protein, there's a coating of SDS just to provide the negative charge. So this is the kind of negative charge that is provided via SDS. So the SDS protein, the protein that is loaded over here, when it moves through the stacking gel, when it moves through the stacking gel, we all know this stacking gel along with the buffer that is provided within the cassette has a glycine residue within it. Now at pH 6.8, the glycine becomes zwitter ionic. The glycine becomes zwitter ionic. That means no net charge. Whereas as tris HCl is applied while preparing this gel, that HCl dissolves into H plus and Cl minus. And this Cl minus, it provides a partial negative charge and it is ionic in nature. And as the protein being negatively charged moves from the negative end towards the positive end, so what will happen? First, Cl minus will move, then there will be loaded, there will be loaded proteins. Cl minus will be there, then there will be loaded proteins, And after that lies our glycine residue. So, in this context, it is stated that Cl minus is the directional component because it is determining the direction. Next, the glycine in its zwitterionic state in its is a trailing component because it is the last thing that will come, and the intermediate stage will be our loaded proteins. There will be our loaded proteins. So therefore, our loaded protein will be in a state of sandwich in between the glycine, which is at the beginning, and chlorine at the end. And therefore, in this way, a more organized, a more organized approach of protein is observed within these stacking gels. And hence, there will be a synchronous entry. There will be a synchronous entry of protein within the resolving gel from the stacking gel. So, if we summarize the entire thing, first of all, protein is loaded. Each of these proteins should be provided with a negative charge, and that is done with the help of SDS. Secondly, these loaded proteins are first of all loaded within the stacking gel. The stacking gel has a pH of 6.8, and when the buffer, the running buffer, is added to it and it is being connected with a power bank, what will happen? Initially, the protein is negatively charged and therefore it will move towards the positive end. This is the first thing. Now, while the movement is occurring and as the buffer added has a glycine residue and the pH is 6.8, so the glycine residue at pH 6.8 will become zwitterionic. So therefore, its net movement will be very less. But on contrary to that, the tris HCl, while preparation of this stacking gel, consists of a Cl minus ion. And this Cl minus ion, being ionic in nature, will drag the entire protein that is loaded from the negative end towards the positive end. So therefore, based upon the repetitive movement of Cl minus and the dragging movement of glycine will help the protein to be synchronized in a more concentrated manner, will be synchronized in a more concentrated manner within the stacking gel. And this will help the entire protein to move from the stacking gel into the resolving gel. This is the basic principle. After entering the resolving gel, we all know its resolving gel has a pH of 8.8. Now, what will happen then? Resolving gel has a pH of 8.8. At this pH, the glycine will become negatively charged. And as glycine will be negatively charged and followed by chlorine, which is also negatively charged, so the movement of protein mediated by glycine as well as chlorine is very compact. And as the acrylamide concentration within the resolving gel is highly, the concentration of resolving gel is much more compared to that of our stacking gel. That's why in resolving gel, the separation of proteins will occur based upon their molecular weight. So, larger the size of the protein, larger the size, we will observe it, we will observe this protein, we will observe the protein over here. And smaller the size, we will observe the protein over here because its movement will be much more rapid. So smaller the size, rapid the movement, larger the size, slow will be the movement. This is how the mechanism of resolving and stacking gel will help to identify a protein based upon its electrophoretic mobility.